Hi students, welcome to Year 11 Chemistry and the Properties and Structures of Matter. This is video number 26 and we're going to have a look at ionic networks. In the last video we started to look at allotropy and just some of the ways in which we can have changes in the bonding between atoms manifest. But I gave you really a very general overview in that video. This time I want to start looking at some things in a little bit more detail. In order to do that, I've started with ionic network solids. So ions are probably one of the easiest things we can understand in terms of how things bond together, because ionic compounds are lattices of positive cations and negative anions. And these are held together simply through electrostatic attraction. And one of the important things to remember about this is that if a particular sodium atom with one, say I'll put 281 here, and a particular chloride atom with 287 were to have an exchange of an electron, so an electron moving from the sodium to the chlorine, this loss of an electron would make the sodium positive and the gaining of the electron would make the chlorine negative. But what then happens is that each chloride ion is then attracted to all of the positively charged sodium ions in its vicinity. So it doesn't just hang around with the particular sodium that exchanged an electron with it, it hangs around with all of them. And this is what creates these networks. So the little pink ones obviously are the sodiums. And this is what creates the networks. These are called network solids or arrays because they are just repeating ordered crystals. So we can get a very strong sense of the fact that each of these negatively charged ions is attracted to a positively charged ion. Obviously the sodium losing an outer shell electron has now gone back to only two shells of electrons, so its radius has shrunk, which is one of the reasons why these ones are shown a little bit smaller, and the chlorines are larger as a result of that extra electron and a little bit of extra negative repulsion happening out there. One of the other things to notice about this too is we've kind of drawn all these really big bonds in here, and obviously that's not the reality. These are regions, they're clouds where the electrons are located, and there certainly wouldn't be these great stick structures between each of these atoms, but it is a way of showing the regularity in each of these crystals, and the fact that each of these negatively charged ions are attracted to a positively charged ion. Now, one of the things we want to do when we start looking at bonding is how bonding relates to properties. The fact that we have such strong bonds, which are ionic, makes them very, very difficult to break. And that means we need a lot of energy to melt an ionic solid, and even more energy if we're going to boil it. One of the problems, though, is whilst they are hard, they're also very brittle. And if I kind of put a simple diagram together that kind of shows the way that this would look, where we have, say, chlorine, sodium, this is where the bonding is. But if you were to hit this with a hammer, say, and just slightly displace this a little, so if we have the large and the small, and just as this gets pushed down, then we would have two little small ones, two big ones, and two little small ones. Now these are now two sodiums next to each other and two chlorines next to each other, and they're going to repel. So what's going to happen is that the crystal is going to fracture or shatter at that point, and that's one of the reasons why these crystals are very brittle. Despite the fact that they have ions, the ions are all locked up in bonds. So in the solid, they will not conduct electricity. There's nothing to move. The electrons are held within the ions, and the ions themselves are not free to move. But if you melt them, then when they are molten, when they are in a liquid form, then the ions are free to move and they can therefore migrate, sodium ions or chloride ions. This is also true if you dissolve them in water. And many, though not all, ionic solids are soluble in polar solvents like water. Their positive and negative nature, though, means they are not soluble in non-polar solvents, and we'll have a look at some examples of that later in the course. Thanks for watching.